Good afternoon, everyone. Thanks for joining us today. I'm Swapnaya Sarapu, and
This is Shruti Sethi from Azure Storage.
we're both here to talk about the opportunities for sustainability, especially as it pertains to cloud storage. And as one of my esteemed colleagues in the back told me, it is post-lunch hour. We're going to try our best to keep you awake and not fall into slumber. So let's keep it interesting. So what we want to do today is to share with you, what is the landscape for carbon emissions, why sustainability is an important initiative, what are our goals when it pertains to sustainability and for our carbon goals, both for ourselves at Microsoft and also, of course, what we can do broadly at the industry level. And then what are some of the opportunities that we can bring as it pertains to storage to the table in order to reduce our overall carbon footprint. With that in mind, let me just ask by show of hands, how many of your organizations talk about sustainability? Oh, that's awesome. Awesome. Okay, that's really great. And how many, again by show of hands, of your organizations have stated sustainability goals? Okay, so we got some work to do, but it's pretty good, pretty good. That's awesome to see. So why are we focusing on sustainability? So this is an industry report that talks about, on the left side, the growth in the overall carbon emissions. Right? And what this is saying essentially is that we're going to go 4x in the next 20 years. That's a pretty big increase in terms of our carbon emissions footprint. Now, on the right-hand side, this is a show today, right? As we look at it, standing in today's days, who or which industries are the largest contributors to the current emissions? And of course, like the biggest two are transportation and electric power, transportation being the bigger. And what it doesn't show today on this chart is the contribution of ICT. However, that 4x growth, the biggest expected contributor to that 4x growth from a carbon emissions is from the IT and ICT industry. So as we look fast forward 20 years to the right, we as an industry will have a pretty big share of that pie that's going to show up. That it's not showing up today, so it's our responsibility to actually do something about it and make sure that doesn't come to fruition. Now, and that's a driver for, from a market perspective, the opportunity for what we call as the green data center, or what Fortune Business Insights calls the green data center opportunity. And what this says is, in the next 10 years, we expect the green data center growth to be over 17% in CAGR, going up to over 200 billion in total market opportunity. So, we can do right by the earth and hopefully also do right by our businesses if we do this right. So from an industry perspective, I asked this question earlier, how many of you actually have sustainability goals? And it was great to see that. So yes, we as an industry are doing, are making the right steps in terms of setting up carbon emission reduction goals. There's a number of companies, Microsoft, of course, being one of us over here, that have stated sustainability goals. And you see that there is a progressive goal that accumulates to net negative carbon emissions. That's why you see, for example, Microsoft having goals for 2025, 2030, all the way up to 2050. So it's a journey for all of us. We certainly are at the onset of it. So there's work to be done overall. And we wanted to share a little bit in terms of what our thoughts are around it and how we can get there going forward. Before we get there, I wanted to share with you what the Microsoft sustainability goals are for 2030. And the three main ones are, we'd like to be carbon negative, water positive, and zero waste by 2030. These are our main 3 goals. We do have other tertiary goals, but these were the ones that kind of stand out for us the best and are the guiding light. Now, of course, if we move forward to 2050, we have an overarching goal where we would like to remove carbon from this environment cumulatively to compensate for all the emissions that Microsoft as a corporation has made since its inception, so since 1975. And that's our overarching goal for 2050. Hopefully some of us will still be in the industry working and making that happen as we move to the right. But this is going to be a multi-generational journey for all of us going together. So Shruti is going to take us and deep dive into what this means to us and take it from here.
Yes. So let me first take a few minutes, and I want to set the foundation for understanding some of the carbon emission categories that will be used in the further discussion. So we are going to talk about 3 categories of carbon emission: Scope 1, Scope 2, and Scope 3, as you see here. So let's look at Scope 1. We indicate it by the word burn, and that's essentially carbon emission occurring due to any combustion that we are directly doing. So if you are running a car and fuel is burning in the car, that is your Scope 1 carbon emission. If a data center has a generator that is burning fuel, that is their Scope 1 carbon emission. Let's go to Scope 2, indicated by the word by over here. And the reason it says by is that's essentially the emission related to electricity, power, steam, anything that is bought to run the systems. So all the emission that occurred when that electricity was generated, again, that becomes the data center's Scope 2 carbon emission. And lastly, we talk about Scope 3 carbon emission to set the foundation for Scope 3. It is indicated by the word beyond here, and the reason is it's a very broad category. It includes emissions during component manufacture, as well as emissions during, say, an employee takes a flight for a business purpose. Like you and I, if we take a flight to come to this conference, and that is sponsored by our company, that is the company's Scope 3 carbon emissions. So burn, by, beyond. So just so that we have that understanding of what is going into Scope 1, 2, and 3. We will use these words in the further discussion. On the right side, before I move to the next slide, on the right side, you see subcategory of interest mentioned over there. So Scope 2, because it is related to the operational time when the power is being used, we'll be referring to that as operational carbon. And within Scope 3, a subcategory called embodied carbon is what we will concentrate on, which ends up being a large contributor for data centers. I will go in depth about embodied carbon ahead also. Okay. So this is Microsoft's Scope 1, Scope 2, and Scope 3 carbon emission from the last year 2022 report. And now that we know what Scope 1, 2, and 3 signifies, so, burn, by, beyond. You see, Scope 3 is actually the biggest target or the most damaging component right now. And for those of you who were in the keynote talk related to carbon measurements, you'll notice that these numbers sort of jive with that automatically because the operational, which is Scope 2 here, is roughly 25%, little more than 25%. Scope 3 is a lot more, about more than 70% over here, which jives with the kind of industry observation that you had in the keynote also. So our first thing is noting that Scope 3 is the largest emission, something that we need to work towards. This Scope 3 includes the embodied carbon that we spoke about. Scope 2, shown in the red sector, operational carbon, will be our second target. Okay. Now let me jump into particular growth of storage and growth of storage carbon. I'll just quickly go over this. I think it's not alien to anybody over here. The storage, the total data being produced is continuously increasing, and it's predicted to be 175 zettabytes by 2025. Correspondingly, there is also a push for more storage capacity being installed, and that's just under 5 zettabytes by 2025. So there is a lot of storage infrastructure going in. With this storage infrastructure going in, we are naturally increasing the carbon we are contributing due to that. And that's the part I'm going to double click into. Okay. So think of two buckets of carbon contribution that the storage infrastructure is making. These are the buckets we briefly referred to previously. The left bucket says scope 3 embodied carbon. Embodied carbon is all the carbon associated with right from mining of the materials, manufacturing of the devices, components, installing the components, and also their end of life. The right bucket, which says operational carbon, the right side bucket, that one is actually referring to the operational phase, more related to the power utilization. So we have the two buckets that we are going to look at, which is adding up to our total carbon. Left side is embodied carbon due to the manufacturing. Right side is operational carbon. Okay. On the left side of the slide, we see something quite familiar. We call it total cost of ownership. And we are used to seeing, okay, there is an upfront cost, there is an operation time cost, and my total cost of ownership is the addition of both of those per unit performance, depending upon whatever the device is. We need a similar framework to look at the total carbon cost of ownership now. Just like we have upfront cost, our embodied carbon is nothing but the upfront cost. That was related to getting the materials, manufacturing, installing. So that becomes our upfront cost, embodied carbon. And then there is an operational cost. Similarly, there is an operational carbon emission. We need to look at a summation of that to get to our total cost of carbon ownership, again, per unit of performance. Let's keep this framework in mind. And we also looked at the growth of storage and the two buckets of storage, the two buckets here, that are contributing to carbon. And let's double click into some of the storage components, some of the categories of storage components. So we'll do a relative comparison of how these are affecting carbon emissions, mostly in storage infrastructure. Before I go to that, I want to highlight a certain limitation though. So currently, there is a limitation on comparing a number of storage components or components in general due to two reasons. One is lack of ready carbon assessment reports for these devices. I'm sure folks who said that their industry or their company or organization is already working on sustainability, you're probably talking about the reports. Maybe some of the companies already run LCA, that is lifespan assessment, life cycle assessment. Maybe you already run LCAs, but the sharing of these carbon assessment numbers is not all standardized in the industry. The methodology of running LCA, which gives us the carbon assessment, is also not standardized. So if I am looking at carbon emission numbers from maybe one HDD supplier and another HDD supplier or another memory supplier, trying to make sense of all of that, it is a little bit like comparing oranges and apples instead of, oranges and orange. Okay. So our attempt here is to run a similar assessment methodology on all of these category of devices so that we can come to a comparison of these categories. Okay. Now I'll go over the comparison in the same two buckets that we discussed, embodied carbon bucket and operational carbon bucket. So first, let's look at the embodied carbon. Okay. So one thing that is generally seen is that more the silicon that is involved in the device, the larger is its embodied carbon impact. You will see some of the things like SSDs, memory over here says higher embodied carbon impact. There are other factors also, like how advanced the technological node is, that can affect whether it is lower or larger carbon impact for that device category. Correspondingly, if I compare the same category of devices for their operational carbon, there will be some devices such as processors and other ICs that might be high power usage, and they naturally contribute to a larger operational side carbon. Once we are comparing all of these devices in the two buckets, there is a third leg that we need to include in order to have a holistic view. You might have devices that are maybe low on embodied carbon, they are low on operational carbon, but what if they are deployed a lot in the storage infrastructure? So our third leg essentially is looking at a proportion of how much of storage fleet, and this is global fleet, generally gets occupied by each of these device categories. So in order to understand what is the real carbon impact by these categories, we need to take into account both the buckets, both the important buckets of carbon emission, as well as what proportion of infrastructure actually includes these devices. Chassis. Yes. So, yeah, we have not actually categorized up to that granularity level. There are a number of, okay, so the category that I say chassis over here is actually not just alone chassis, but it includes a number of others. Yeah. You will also find there are some product categories not yet included. And that's, like you're saying, it's not to that granularity level, or there is a product category that we haven't yet in depth looked at. Okay, with that understanding, I a little bit want to jump into what kind of opportunities we as an industry could have in order to reduce our carbon emissions. And we'll again talk about some things that we can do in a shorter term, and then maybe a longer term, bigger hammers that we can use. Okay. So first, the opportunities for our bucket number one, that was the embodied carbon. Okay. Let's think of three particular aspects. First one, which is designing for longer device lifetime. Now, this is not something alien, essentially. If I give you an example, if somebody worked on software to improve the write amplification and it reduced the wear out, it is increasing the lifespan of the device. So what I'm trying to say is it's not something that is absolutely alien. We just have not connected it to carbon yet. Of course, there are other initiatives that can happen to increase the lifespan. Maybe there is some kind of new material usage that could be looked at. But yeah, a lot of the lifespan assessment, if we think about, we'll be able to connect our current work with carbon. The catch here, though, is when we deploy the devices for a longer period of time, we have to be mindful of the fact that A, they are still delivering the required key metrics of performance, and B, they are still satisfying power usage. So if I'm deploying an older device that is maybe extremely power inefficient, then it is reducing embodied carbon, but it's increasing operational carbon. So we just have to be mindful of these. Second aspect, so we talk about reuse enablement here, so circularity. For storage specifically, one big thing in device circularity, and this is storage media circularity, is being able to confidently and securely wipe the data that exists. And you must have already noticed that I emphasize the word confidently and securely. And the third aspect we'll look at is basically thinking about the recycle enablement. Now, as far as carbon savings go, reuse or extending lifespan gives you better carbon results compared to recycle. Due to very obvious reasons, because when you have to recycle components, you have to do another process, maybe to separate out components or to separate out materials, and that will take energy. But still, recycle still gives you a certain amount of carbon savings. It does require that devices be architected and maybe structured in a way that might be easier to open, separate out components, maybe recycle just subcomponents. Okay. I'm going to go to the other bucket. And the other one is the more familiar, I think, power operational carbon bucket. Again, looking at three aspects mainly. First one, improving the power telemetry. So this is to give us an idea of what can be done better to utilize the devices, utilize the power extent of the devices at a system level also. Second one, concentrating on low power states and idle states. I think, so we no longer need to think that data center devices need to be all the time continuously spinning or ready to go. We basically need to be able to give low power states, but of course, looking at manageable latencies. So there is some work required over there. It's not a simple answer, but this is certainly a path that we should be looking at. Third one, and I think the most known and worked on path, is efficient active power usage. So whenever we are in the active power state, increase the efficiency of power utilization. Okay. So both of these sets of opportunities are things we can do in the, I'll not say near future, but comparatively shorter term. There are certain bigger hammers that I would like to highlight. Oh, sorry, before I go to that, I completely forgot to mention one thing, which I've written at the bottom. One reason why embodied carbon ends up being a bigger damaging factor is also because for operational, there is a continuous effort already to go towards renewable energy. So that's like a bolstering, supporting factor that we can work towards. But embodied carbon has more restrictions, something that needs more effort more attention from our side. Okay. Now highlighting some of the longer term, bigger hammers that we could go with. This mainly talks about, completely changing the game, changing the kind of storage media. I've highlighted here silica glass and like DNA or molecular storage. And a couple of factors why these things end up being more carbon efficient is, one, the material might be recyclable. So we are looking at that kind of media where it can be recycled. Second, no power might be required once the write is done. So if the write is done and the data is only going to be sitting there for a long period of time, if that does not require continuous power, that is a big savings. Third one, if the media is long lasting, then it reduces the refresh that is required. And not doing refresh saves power. It also saves the media material. So all of these factors contribute in making these storage media lower carbon footprint. Okay. With that, I would like to wrap this up. Just giving a call out for the three main higher level themes that we see over here. For the shorter term, we do need to design for reducing embodied carbon, reducing operational carbon. And remember that it is not so different from what we are working on. We have just not connected it to carbon. Just like I said, reducing the write amplification, it actually helps carbon also. We are not able to see that yet. And then the third point, highlighting that we look at some long-term, large hammers going towards media that is lower carbon footprint. That's it. Thank you so much, folks. And happy to take any questions. Yes. Yes, go ahead. Yes.
So energy is an OpEx thing. The peak power that you have to design for is a CapEx thing and increasing the embodied carbon. So the classic example is if you had a server that you, at peak power is 2 kilowatts, right? And you've got another one that's 1,000 tons. You run them both, you run the 2,001 for 2 weeks, you run the 1,000 watt for 4 weeks. The energy usage is the same.
Right.
But all the way back upstream, back to where you designed the generating plant, you have all that embodied carbon, you have to pay for it. It's a CapEx that you then have to amortize financially and carbon. And so some of that has to be done with load shifting and figure out how you're going to take the components you use and use them at closer to 100% rated capacity all the time.
Yes. So, oh, sorry.
And by the way, you do get first, if you just only know about your residential energy, you never see that. But on an industrial basis, you pay what's called a demand charge. And that can get hella expensive, especially in places like Silicon Valley. But that's because the generating, the power company has to amortize the transmission lines and everything else that they have to build out to serve your peak plant, not your average. So it's a big deal that gets ignored.
Yes. So, first of all, to sort of summarize your question, was that instead of looking at power, we should be looking at, what is the energy getting utilized. And when we are taking an example of, 2 different components or servers that are operating at a different power level, it basically means we are going to pay for the power allocation and all the infrastructure that went in according to the one that is running at the higher power level. Now, that is certainly an aspect that we actually look at, and that goes into, trying to make sure that our systems running at, I'll say not 100%, but the maximum possible workload, so that efficiently sort of, equalizes the utilization everywhere. The reason I didn't touch upon that right here is because we are looking at that more at, a system level on our side to be able to, than, asking for help to do that, is why I didn't touch upon it. Yes, go ahead.
On your design for reading mandate, do you have a feel for what percentage of the fleet, say your premium storage, goes to a secure byte reading today?
Yeah, I can repeat the question. So you're basically asking what percentage of our premium fleet is going through a secure wipe, data wipe today. I don't think we are at a liberty to share that information, and that's why I said I can repeat the question. But let's say, like, we are certainly looking at trying to have the data wipe and reuse. And that's why I raised that point that we need to be able to confidently and securely wipe that. I know, like, a lot of drives have put in the capabilities of doing some wipe. There is some more work in the verification part of whether the wipe has or sanitation has gone through securely. Like, there are a couple of modes, whether we do, host write based wiped or crypto erase. But there is some more work in the verification part to give the confidence that that is working completely. And that's sort of what we are looking for. I mean, we're certainly in that.
I think put another way is we can expand the use or the breadth of that reuse based on how much more confident we can get in terms of the wipe capability of the media itself.
Yeah, I was just trying to get a sense of whether you have anything today that has given you that confidence, whether it seems like not there.
Yeah. For certain use cases, but certainly not where we want to stop with it.
So kind of on that, like, let's say you want to use the old hard drives that are 5 to 10 years ago, and they're supposed to be 5 to 10 years ago to be 2 terabytes, and today's capacity is 3 terabytes. And the power consumption is maybe the same of those versus the new ones. What is how are you evaluating the cost, the carbon cost to use?
Sorry, please finish your question. I want to bring it here.
Okay, how is that the cost, the comparative cost for either, reprogramming the variables or running them at a lower efficiency, but because we have the sunken cost already. So what is the evaluation for that, and what is your option that you're exploring? Like, for example, as you said, either sanitize them and pass them on to someone who may have a better use case for it, or is there better internal use cases? This question is like that.
Okay. So, yes. So let me repeat your long question. So as a gist, you're basically looking for when we are reusing any kind of older hardware, and it might be at a lower capacity or performance, how are we evaluating in net total, whether, with carbon and maybe other factors, how are we evaluating whether it is worth to go ahead? So let me answer that point first. So actually, this is a very important point that you pointed out. Like, when you try to use an older hardware, you have to not only take into account that it might be less power efficient, but also that, like you said, a lower capacity. That essentially means now I need more space, for example, in the data center, to service the same, set of total customer ask. So it's not just a very simple math of, okay, power plus capex, power plus upfront cost in terms of carbon, but there is an additional of, okay, now you look at how many other racks or how many other systems can I not deploy because the space is now utilized. So the right side framework that I show over here, it is a very simplified version just for the slide. But the actual TCO or TCCO that you would try to calculate for this, total carbon cost of ownership, would have to take into account that I'm not just using more power, I'm using more space here, right? And at data center level, you have certain other metrics that the industry is defining, not just PUE, which is for power, but also like IUE, that is infrastructure usage efficiency. And that concentrates on, things like you are mentioning. So that brings all of that factor together.
A couple of more points to add from that perspective. As we want to extend or reuse, one of the areas where I think we as an industry can do well is to figure out what is the ability to reuse the component, right? What is the PFA capabilities? How much more life can be had? How well can we predict? And I think any efforts that we make to bring more visibility into those metrics, I think enables us to come up with more use cases. And of course, your question around how confidently can we erase data is spot on, right? That ties back into it. So those are kind of the two other technical aspects that also we can work on to move that forward.
Yes, go ahead.
So you talked about there was no standardization on the measurement and the reporting. Can you expand on what you expect the future to bring in that standardization?
Yes, sure. So the question is, we spoke about lack of standardization for running carbon assessments and sharing carbon assessments. So where do we want to see that go in the future? So essentially, although there are some, I'll say, standardizing bodies, like there is, I want to say, ISO 14040 that talks about how the LCA assessment should run, but it just doesn't go into complete depth of all the attributes of running the LCA method, which allows some variability. And once there is this variability, a carbon assessment that maybe you run on the same device and I run on the same device might not give similar numbers. Where we finally want this to go is so that assessing carbon, or I will call it should become measuring carbon instead of assessing, which means something that we are very comfortable with, just like measuring power. Like your power measurement and my power measurement, we expect it to be very much in sync because that is how the measurement is defined. So once this standard can be agreed upon between the industry so that we know that whether you run the process or I run the process, it is going to be following a similar kind of methodology. And then we can actually exchange the carbon numbers. Like, it doesn't have to be that we try to run on every category of components. Because if you are running with the same methodology, then we are happy to, just look at the numbers that you are providing. So that's hopefully where we want this finally goes to. So, yep.
There was a table in your presentation that says major carbon contributors of storage items. I have a specific question on that. One thing I was wondering was, is this normalized medium, high, low, or I have to look at, like you said, scope 2 is higher than, scope 3 is higher than scope 2 in terms of 70% versus 71% versus 28%, but then when I look at the medium on scope 3 and high on scope 2, is that all normalized in this picture?
Good point. So all the comparative mentions, repeat the question. So I guess the question is that in this particular table that is comparing the scope 3 embodied carbon, operational carbon, is it all normalized to one scale?
Row 1 is a different scale than row 2, or they're all the same scale?
Yes, and very good question. Row 1 is actually a comparison within itself. So the entire blue writing that you'll see in row 1 is a comparison within itself. It will be a different scale than the orange row. And that is because operational carbon itself is a smaller section than, our embodied carbon problem. So within the row, though, they are all normalized, and that is how we are giving a qualitative. That is right. The higher of a scope 3 will be higher than a high of a scope 2. If that's so. Oh, medium. Medium scope. Oh, okay. So I think that part I will not delve into right here. And the reason being is, the reason I kept it a qualitative comparison is also because LCA methodologies are, I'll say, less standardized right now. So there is some variability that can occur, but this is to give us a first approximation of where we are going. And given we look at not one, but multiple LCA methodologies and try to reconcile with them. Go ahead. When you say for processing, you mean for manufacturing? Oh, okay. Oh, I see. Okay. Okay, so if I repeat the question and also correct me if I caught this one right, because I'm not sure. You're sort of trying to understand the range for memory and maybe of the other storage media. Is that right? So I can talk to you right now about some of the factors that actually help storage media that don't help the memory so much. And correspondingly, there are factors that help the processors that don't help the storage media so much. One thing is, just like we have economies of scale in a lot of other things, you actually do have some effect of economy of scale here also, which means storage media, which sits, which is used in much higher capacities than DRAM memory is used. That is one major reason why memory gets hit by carbon a lot more. So you are running the entire process and maybe only manufacturing, a small 256 GB compared to I'm running the entire process and I'm manufacturing something like 16 TB. So there is an economies of scale factor that helps the storage media compared to the memory. I don't think I can go into specific numerical values, but that's sort of to give you an idea why memory is on the high with the embodied carbon. Okay, so the question is it the same reason for SSD and HDD? You also mentioned SSD is lower in usage? Okay. Right. Okay. Got it. Okay. So the question is also that, is it because the capacity that is deployed in SSDs today out there is lower than what is deployed on HDDs? That particular thing is actually indicated in the third row. And that is why we introduced the third row, where you have to look at how much of it is actually out there, in storage kind of infrastructures. However, when I'm talking about it in the first row, I'm not actually looking at the total out there deployed. One reason why you see a high over there is it is seen that more the silicon that is being used in the devices, it actually has a worse impact on the embodied carbon. That's where you get that from. Yes.
Question, do you plan to add also a closed tape?
So I was just wondering, nobody asked about it. And specifically, no, I was actually thinking about you folks. But, okay, so to repeat the question, is there a plan to add tape in the entire comparison? So like I was saying initially to SW also, this is not a complete study and doesn't have all the granularity yet. And that's the reason tape is not here. I think we are not at a place to, have a relative comparison yet on that part. But yes, thank you. Sorry, go ahead.
When there was one slide where you said going to idle states with acceptable exit latencies. So that's an example of where you're accepting some kind of reduced metric. So I'm kind of curious where else can we expect some relaxation to get some of these advantages. Is that the only one we can either achieve these without other leeway?
Do you want to take it?
Sure. So I think your question is the idle states and the low power states with manageable latencies for the system. What does that show up itself or embody itself as, right, as an end state? It's a hotly debated topic because we cannot go back on our customer promises, right? So that's why when we talk about manageable latencies, what it basically means is it's customer invisible, right? So it's an area where I think there's more work to be done. We have found a few initiatives that are, kind of in the flow, so to speak, where we're able to talk about some of the L states, right, and the exit latencies associated with it on certain portions of our portfolio, but certainly not something that, right, applies all the way across to storage. So we're open to ideas here on how you can manage customer promises while taking advantage of some of the low power states. I think Damien went, yeah.
Yeah. Yeah. So to repeat the question, it's about that, the scope 2 or operational that we showed is only a quarter or a little more than a quarter. And the scope 3 or which includes embodied carbon, that scope 3 is almost 3/4. So shouldn't we be working on that? And actually, we completely agree with that point of view. And that's the reason why I also mentioned this at the bottom, that there is some other effort also that is bolstering or supporting this particular operational carbon side, but we have, I'll say, more hands tied on the embodied carbon side. So we do need more attention to that. I completely agree with, yes, that's what we're trying to say too. Yes. Sorry.
On your previous slide again, back to that slide, I think this is a snapshot of today, but I'm guessing this is going to change a lot with AI and everything else. And what is your projection for those slides so that rather than skating to where it is now, why not skate to where the past is? So what is the projections that you expected, and how do we now meet those needs?
So to repeat the question, first of all, the question was about, this is some of the analysis that is as of today. And then as we are moving ahead, there is a lot of AI growth, etc., that we are seeing. So how do we plan of looking at that aspect? And I think the way I want to sort of put that is, so we see growth in a particular area, and we as an industry run behind it, which is great, which is certainly needed for progress happening and in general growth happening. All we need to do is right now we are not looking at the carbon along with that. When we run towards growth, we look at the cost. We still have that dollar per TB or dollar per TB per some time duration in mind. It's just that we are ignoring the the kg CO2 emission per TB. So it's about a little bit of change of approach. We are going to move towards growth. You don't want to say that, don't have carbon emissions by not growing. That would essentially, not be good for mankind. But what we are trying to do here is that as we are approaching this growth, we are constantly being ahead of the curve and thinking, just like you said, that, okay, tomorrow AI is going to be deployed this much more. That AI uses so much more storage. How can I make that particular storage more efficient? Or, when it is basically having all the read accesses during ML training and it's reading this entire chunk of data, how can I make that more efficient so that it, uses less in terms of storage resources? That's sort of where we are targeting, and we are certainly thinking in that direction. Yes. So the question was, are there other sides that we are looking at, which is, maybe electronic waste, etc. So one, certainly waste actually, adds on. If you remember, when I briefly described embodied carbon, I spoke about materials, manufacturing, installation, and end of life. So there is a component related with that end of life process also. So one is we are continuously trying to reduce the waste, and two ways of doing that is enabling the reuse or enabling a recycle of part of the components. The aspects that sort of hold up in that, one is the technical side of aspects, like I said, that when you are reusing, you have to take care of the other aspects, other performance and power, etc. And then there are some other financial aspects that you have to take care because you are using an older device. But we are certainly actually concentrating on, reducing the waste and enabling circularity. Like circularity is our thought process of reducing that direct to landfill waste. Microsoft actually has 5 circular centers right now set up, which are mainly for being able to see what are the devices that are finishing their regular production life can actually be reused or looked at for any other work instead of directly going to landfill.
Thank you.
Thank you.